PreCalc, what's up? Here we are with day 2. Yesterday we got our tests back and we got just a little intro into limits. We had a story problem here where we're trying to maximize the area given 24 inches of wire. Alright, and we saw that as our width and length both came into 6, the area got bigger and bigger and bigger and maximized there at 36. Okay, then we looked at finding the limit for a linear function, 3x minus 2. We wanted to find the limit as x goes to 2. So we made this table, and we saw that as we got closer and closer to 2 from both sides, our y values were converging on 4. Okay, and this one, yes, would have been easy just to direct substitute in 3 times 2 minus 2 is going to give me 4. But then our next one was a bit of a problem. The limit as x goes to 0 of x over the square root of x plus 9 minus 3. If we put 0 in, we get 0 on the top, and then we get 3 minus 3 on the bottom. So we would have 0 on the bottom as well. And we can't have 0 divided by 0, so we made our little chart, and we saw that our values, as we get closer and closer to 0 from both sides, are going to converge on 6. So the limit as x goes to 0 would be 6. So the limit is kind of like what it's approaching, what it's coming into from both sides, not necessarily what does it equal. All right. Let's have you try this one, example 4, putting those in, and when you get done, hit pause and put those in, and when you get done, push play again here, and we'll have an answer for you. Let's see how we did. So if we put 1.9 in there, we should be getting 5.6, 5.61, and 1.99 gives us 5.96, and then we would get 5.996. And it looks like we're getting really, really close to 6. Can't just directly substitute 2 in, because if I put 2 in, we're going to have 0 in the denominator. We can't divide by 0. Let's go the other way. 2.1 is 6.41. 2.01, 6.0401. And if I put 2.001, we have 6.004. So, yep, it looks like it's coming into 6 from both sides. It's approaching 6. So the limit as x goes to 2 of x cubed minus 2x squared plus 2x minus 4 would be 6. Find the limit of f of x as x approaches 5, where f is defined as 1 for everything when x is not 5, and negative 2 when x does equal 5. So everywhere it's 1, except for at 5. At 5, it is negative 2. And this is some tough lines to read here. So everywhere else it's 1, but we got an open dot there. And then we just jump down to negative 2 right at 5. Well, what would the limit be as x approaches 5 then? If I'm coming at it from the left side, we're at 1, 1, 1, 1, 1, 1, 1. If I'm coming at it from the right side, we're at 1 the whole way. So the limit is actually going to be 1, even though the actual function value jumps down to -2 right there. As we're coming in from the left and from the right, we're all 1s. So the limit is 1, because that's what we are approaching from both sides. Show that the limit of absolute value of x over x as x goes to 0 does not exist. Okay, they have it graphed for us over here on the side. Okay, as I'm coming in from the left, what does our limit look like it is? -1, -1, -1, -1. So from coming in from the left, it's -1. Coming in from the right, it's +1. And they don't match up. We're not converging on one value. We're not approaching one value or the same value from both sides. So we are not going to have a limit. So let's see here, some fancy notation. The limit as x approaches 0 from the left, negative sign there, it's coming at it from the left side, is -1. The limit as x approaches 0 from the positive side is 1. Don't match. So we would say the limit as x approaches 0 of the absolute value of x over x does not exist. D-N-E. Does not exist. There we go. So if they don't match, it won't exist. So we have some more DNEs coming up here, just examining some rules here that we have for limits. So if it doesn't match, it does not exist. What about the limit as x approaches 0 of 1 over x to the 4th? Let's take a look at this graph. 1 divided by x to the 4th power. Okay. As x approaches from the left, it shoots up to infinity forever, and from the right it also increases without bound. Okay? So it goes up forever towards infinity, and it does not approach a unique number. Approaches, well, increases without bound is probably the better way to say it. Increases without bound from both sides, does not approach a unique number. So, does not exist. Okay, we're not converging on a unique number there, so it will not exist. Another one, the limit as x approaches 0 of, for cosine of 1 over x. Let's see if we can get it to do it there. No, let's see. We'll change it to degrees. radians. Okay, so that's what we're looking for there. So if it starts going crazy at the number that we're approaching, so as we're approaching 0, nice and smooth, you're like, oh, this is going to be like 1 or something here. It's just coming in nice and smooth, and then it dives down, and it's like, okay, so it's bouncing back and forth crazy. Then you're going to say it doesn't exist because it's not approaching a unique number there. It just starts bouncing back and forth, so it's not necessarily just smoothly coming in to a number. Okay? As you approach 0 from both sides, it oscillates between -1 and 1, so it never approaches a unique number. Limit does not exist. As it approaches 0 from both sides, f of x oscillates between -1 and 1. It never approaches a unique number. So that's another DNE. Does not exist. Alright, so we've kind of talked about these here with examples, but there they are again, the conditions when it does not exist. If it approaches a different number from the left side and the right side, if it increases or decreases without bound, or if it bounces back and forth between two values, it oscillates quickly there between two values, then we're not going to be approaching a unique number there. It's just bouncing back and forth, it's going crazy. So we're not going to have a limit there either. Okay? You've seen that sometimes the limit of f of x as x approaches c is just simply f of c, as we found in example 2. In such cases, it is said that the limit can be evaluated with direct substitution. You're just going to plug the c number in there. There are many well-behaved functions, such as polynomial functions and rational functions with non-zero denominators that have this property. Okay, basic limit here, blah, blah, blah. If you're doing the limit as x approaches c of a constant b, so like the limit as x approaches 3 of 10. It's always 10, so the answer is 10. The limit as x approaches c of x, so that your equation is just y equals x, then your limit is going to be c. Exponential equations, you just plug the number in for x. And then for roots, again, just plug it in for x. But for even roots, the c has to be greater than 0. We're not going to mess with imaginaries with our limits here. Properties. Okay, we can multiply by a scalar. We can add and subtract two functions. We can multiply, we can divide, and we can do powers. Alright, so direct substitution here, these are as easy as they look. These are as easy as they look. Okay. Limit as x approaches 4 of x squared is going to be 4 squared 16. Alright. These are as easy as they look. Go ahead and give them a shot. Push pause here. Go ahead and give these a shot. Okie dokes, welcome back. So we're just, again, for most of these here, we're just dropping them in. All right, 5 times 4 is 20. If you put pi in there, tangent of pi is 0, and 0 over pi is 0. We're okay there. Square root of 9, we know that one is 3. Pi times cosine of pi is -1. We got negative pi. If I put 3 in there, 3 plus 4 is 7 squared for 49. Okay, just practicing substituting these in and getting used to getting used to the notations, so no sweat there. When evaluating limits, remember there are several ways to solve most problems. Often a problem can be solved numerically, graphically, looking at the graph, or algebraically. The limits of example 9 there were found algebraically. You can verify these solutions numerically or graphically. For instance, to verify the limit in 9a numerically, create a table that shows the values of x squared for two sets of x values. One set that approaches 4 from the left, one set that approaches 4 from the right, and show with a table, numerically, that we are converging there on 16. And the limits of polynomial and irrational functions. If p is a polynomial function and c is a real number, then the limit as x approaches c of polynomial of x, then you just, again, can just substitute it in. In a rational one, rational functions, we just have two polynomials being divided. Then you can just substitute that in and do the limits on the top and the bottom there and just substitute it in. So some friendly ones here, just as long as they don't equal 0 on the denominator, which they don't. We're just going with some more direct substitution today. Don't worry, things will get more complicated in the future. So we're going to have 2 squared, 5 times 2, plus 4. So we got 4, 10, 4. The limit as x approaches 2 is going to be 18. And then on the other side, well, we have 18 on the top. That's the same one as we just had. 2 plus 4 is 6 on the bottom. And as we approach 2 is 3. Okay? Again, relatively easy stuff today. So just the new stuff is the limit notation and the wording and the idea of it. And then we did have the 3 types of problems there where you cannot have a limit. It's not defined, does not exist. Other than that, we're just getting comfortable with how it looks and practicing substituting in for these basic ones that we can. All right, thanks a lot, folks. Good luck on that homework, and let me know if you have any questions.